Hello, and welcome to the amino acid activity. Today we'll be going over a method that I like to use to learn to draw, name, and learn the abbreviations for each of the 20 amino acids. So let's begin by going over the backbone of the amino acids. Right, so there's sort of two ways to think about the backbone. The basic structure is that it's a repeating unit of nitrogen, carbon, carbon. It goes NCC, NCC to the end of time. And I just wanted to highlight that a couple of details here. So first, the alpha carbon is the name for the middle carbon. That's where the R, or functional group, comes off of. So for every amino acid, the backbone is the same with just one small exception. And the R group is what determines the amino acid's properties. That's the functional group that we're going to be learning here, and it gives it its name. One thing to highlight here is that there are two ways to draw the backbone. You can draw it uncharged, like I have at the top with A here. So the N has two H's in a lone pair, and this carbon is bonded to an alcohol group, or rather a carboxylic acid group. But it's protonated, right? The other way is to draw it with the N having three H's and a positive charge and a deprotonated carboxylate group instead of a carboxylic acid. The bottom structure is more correct because this is how the amino acid would look at biological or physiological pH of around 7, where because the NH3 or the amine groups pKa is above that pH. It's in an acidic environment for it, so it'll get protonated. And the carboxylic acid group has a pKa that is below physiological pH of 7. It's maybe 3 or 4. So it'll be deprotonated because it's in a basic environment. And then one last thing, you'll see used far more than these very large structures will be the simplified structures, where we just replace the carbons with lines. It's just basic organic chemistry drawing. But I just wanted to make you aware of these two variations because you will see these much more frequently than you will see the whole thing with all the atoms drawn out. So let's get into the amino acids. And this is the setup we're going to use. I've drawn a skeletal structure here in the simplified form. And I'm going to be breaking these amino acids into a number of categories that are maybe a little bit unconventional. I'll be placing them in the nonpolar, polar uncharged, basic, and acidic groups like you'd normally see. But for the purposes of learning them, I think there are some more categories that are more useful to think about. So we're going to start with a group that I like to call the simple carbon chain group, simple carbon chain. And it begins with an amino acid that has no functional group at all. This is glycine. Just has an H bonded to the alpha carbon. Oh, let me mark this with an alpha then. And just to keep in mind, there's always going to be a second hydrogen here. I'm just not going to draw it because it would take up too much space. So the R group is just a hydrogen. The name is glycine. And for all of these, I like to say simpler amino acids, the letter and abbreviation usually reflect the name, which is nice. So glycine is G, and the abbreviation is GLY, just the first three letters. All right, so why don't we go ahead and place glycine in our nonpolar group. And it's nonpolar, so obviously the whole amino acid altogether is not nonpolar, but here all we care about is the polarity of the functional group. And obviously H is a nonpolar functional group. Okay, let's reset it. So what could be more complicated than an H? Well, moving along in the progression, the next group is a methyl group, a CH3 group. And this is the group given to the amino acid called, let's put CH3 here, alanine. And just like with glycine, the letter is A. The abbreviation is ALA. Very simple. So we had our CH3 from alanine. Now we are going to start building upon the chain, right? So this time, we're going to branch it off. And because if you sort of trace this out, it forms a bit of an upside down V shape, right? So this one's going to be called, so there's the V shape, upside down. This one is called valine. The R group is a CH, CH3, CH3. And again, V and val, because it's a simple amino acid, so it gets what it wants. Okay, so we have valine, and we're going to sort of build on this to make our next amino acid. And all I'm going to do is I'm going to add a carbon before the V. So I'm going to put this here. Let's add a carbon here. It's going to be a CH2. And it will sort of extend this V downwards. And this is going to get called, so I'll do the functional group again. CH2, CH, CH3, CH3. This is leucine, LEU. Now, you guys may have heard of iso group before. So an iso group is typically where you take a carbon that's bonded to the last carbon in the chain. So not the last carbon in the chain, but the carbon that is bonded to it. And you shift that carbon down to a previous carbon. So let's take our last carbon, one of our two last carbons here. And we're going to shift them down to here. And then I'm just going to rearrange this to make it look a little prettier. And this is now isoleucine. And that is the end of our first mini group of amino acids. And again, these ones are the ones that I just call the simple carbon chain amino acids, because that's all they have. Okay, before we get into our next big group, we're going to cover the first weird amino acid that really can't be properly grouped at all. And this is a nonpolar amino acid as well. And this one is proline. So proline has a ring, right? But it's not an ordinary ring. It's a ring that actually connects to the backbone. So the functional group and the backbone are kind of all one piece. And here's how that looks. So you guys know what a pentagon looks like, right? Like a 5-membered ring in the organic chemistry. This is the same thing. There's also a 5-membered ring. So just happens to include the nitrogen of the amine group. And so obviously an HO to get pulled off here. This is proline. So the R group, there isn't really an R group. I'm not really going to draw one here. It's just kind of a weird big ring. Proline, P-pro. But because it's a simple nonpolar amino acid, it still gets what it wants in terms of its naming. So that's nice. My next group of amino acids are still nonpolar, but these are the two sulfur-containing amino acids. And their names are, well, let's see. So, first one, you can't just put a sulfur on here. That doesn't work for amino acids. So, we're going to have to put a carbon first. And then an SH group. So, if we just put a sulfur, it would have to be negatively charged. So, we'll put an SH there to keep it neutral. So, it's just R, CH2, SH. Name of this one is cysteine. C, cis. So how can we build on that to make a new amino acid that is also sulfur containing? Well, I'm going to add 2 carbons. I'm going to add 1 carbon before the SH and 1 carbon after. So I'll make this a CH2, SH, CH2. We would have a problem here because this S would be positively charged if we kept the H on it. So we're not going to do that. Instead, we're going to chop off the H. So it looks like this. 2 carbons, an S, and then another carbon. So I'll draw it skeletal here. Carbon, carbon, S, carbon. This is like the amino acid. Okay. This is called methionine. met. I realize I should probably be mentioning fun facts here. So methionine is always the first amino acid that gets translated in a protein, because the start codon, AUG, codes for methionine. Cysteine, fun fact, is that it's very important in a protein's tertiary and quaternary structure because it makes disulfide bridges, which are a very important type of strong linkage between two cysteine amino acids when you oxidize the cysteines and bind them together. Okay, our final nonpolar group is the nonpolar ringed group. So nonpolar amino acids that have rings on them. And the first one is called phenylalanine. I'm going to write that out before we draw it, actually. So phenyl, and the name is important here because all it is it's alanine stuck to a phenyl group. And a phenyl group is just a six-membered kind of benzene-like ring. So CH2, that looks like alanine so far, minus an H. And then we just stick on a phenyl group, and that's all. So phenyl group, phenylalanine, here would be the R group. I'm sort of tired of drawing out all the carbons. We're just going to do that. Letter is F. Letter is F because if you take the first two letters, phenylalanine, they make an F sound. So F and then PHE is the abbreviation. Because we usually tend to go as simple as we can be with the abbreviations until we start using up abbreviations, which we're going to see in a minute. So that's going to go here. We're almost out of space. That's okay. Yeah, okay. Now, how can we build on our ring structure here? And I will tell you how. We are going to add another ring before our phenyl group. And I hope you guys can see that this is a pretty common pattern now where we add another group before a group to make a new amino acid. This time, though, it's not going to be one of these simple carbon groups. It's going to be another ring, right? So this molecule, I just forget where the N is. Let's do it here. This molecule has a 5-membered ring, and then the phenyl group comes off here, off from the side that does not have an N and is exposed. So the way, this is one of the ones where you want to practice drawing it. Here's how I'd practice drawing it. I'd actually go from the bottom up. I'd say, okay, here's the base, CH2. Now we're getting into the ring, right? So to the right side, I'm going to go up to the N, double bond. And the left side, I'm going to close it off. And then from that left side, I'm going to draw my phenyl group. Something like that. Okay. So the name of this one is, actually let's show our group first, so I'll do it again. So we go to the right, to our N, to the left, close it off, and from that left side, phenyl group. Name here is tryptophan. So like I tripped over and hit a fan or something. Letter for tryptophan is W. Now that may seem a little bit out of left field, but pretend that you're a little kid trying to pronounce tryptophan before you can say your R's correctly. You might say something like tryptophan, right? Tryptophan. So W goes there. Abbreviation though is simple, just trip. TRP, trip. All right, and that we are almost done with our nonpolar group, which is by far the biggest group. So this will speed up after we're done here. All right, our final ringed amino acid. Let's do it. This one is a bit of a different one. This is histidine. So histidine, H, his, because there have been no H's yet, and there'll be no H's in the future, so we get to use H. Yay. All right, so this is another ring that does end up looking a little bit like the 5-membered ring in tryptophan, in that it has N's and double bonds, but it's overall a little bit different. So let's do this. Okay, first off, we're going to go to the right and immediately encounter a nitrogen. And then immediately after that, have a double bond up to a carbon here. Then on the left side, immediate double bond going up to an N, and then we'll link them all together at the top. Like that. And so this N is going to have 3 bonds and a lone pair. This N only has 2 bonds, so we got to give it an H, so we can have a lone pair and be happy. To practice drawing this one, I would do kind of the same thing. So start with the base carbon. Now we're getting into the ring. So to the right side, it's single N double. The left side is double single N with an H. And then we just link them up. So that's histidine. And histidine is not, in fact, a non-polar amino acid, but it is a ringed amino acid. So I wanted to, for the purposes of drawing it, group it alongside the other ring structures. So I'll just draw it again. Why not? It actually is going to end up falling in the basic group, and I'm going to show you why, actually, before I copy this. So anything with an amine, so an NH group, has the ability to be protonated, just like we saw with our backbone here. And so in sufficiently acidic conditions, which are not very acidic at all, we can add an H to this N, making an NH plus, aka a basic group. So let's put that in our basic or positively charged category. Although it is also ringed, so we can also think of it that way. I'll make these a little bigger. There's only 3 of them. So what could be next? We're now moving on to a group of amino acids, 2 of which we've already seen before, but I think is still instructive to take a look at. 1 of which we've seen before, but I think it's still instructive to take a look at. These are our phosphorylatable amino acids. And what does that mean? Well, you all know about phosphate groups and their importance in inorganic chemistry and biochemistry, like ATP, or when we're linking nucleotides together to synthesize new DNA. Phosphate groups are pretty much always added, if you'll remember, in the example of DNA, it's the 3' hydroxide. In the example of ATP, it's also hydroxide on that second phosphate. Phosphates are almost always added to a hydroxide. And so 3 out of our 4 phosphorylatable amino acids are going to have hydroxides. Seems convenient, right? First one to cover is the simplest, CH2OH. And there's always a CH2 here, right? So we can just leave that in, honestly. This is serine, ser. And that phosphate would be added right onto that last hydroxide, obviously, in the side chain. Cool. All right, how can we add to this to make a new amino acid? Well, I think the simplest way is just stick another carbon on it. This is now threonine. Threonine. Way to remember this one is that the side chain contains 3 major atoms. And the letter, it's not T. Is it T? I think it's T. THR abbreviation. All right. And then the last hydroxide containing amino acid is actually very, very similar to our old friend phenylalanine. So I'm just going to start by drawing a phenylalanine, and then we'll add to it. And I'm doing it this way because I like to think of all these amino acids as being created by adding to previous ones, if possible. So this is tyrosine, and we're just going to pop the OH on the opposite carbon from the place we started here. So it makes like a nice, clean, smooth line. So side chain here. This is tyrosine. Tyrosine. Oh, I think the letter here is T. No, I think it's Y. Let me start checking these things. Tyrosine. So that. And tyrosine is actually usually classified as nonpolar. The reason for that is that the giant phenyl group makes the molecule overall more nonpolar than the hydroxide makes it polar. So, spiritually, it's part of these three because it's phosphorylatable, but it's actually a nonpolar amino acid, kind of over here on its own. And the last one we saw already was histidine, which is here. And the phosphate group is added to this nitrogen here, which is unusual, but happens. Normally, if you're asked about this, the three amino acids that usually get phosphorylated are the three we just covered, so serine, threonine, and tyrosine, but it is possible to phosphorylate histidine as well, just rare. Okay, we only have 3 groups left. Our next group is the amide group. So you all know what an amide group is, right? An amide group in general is just a carbon bonded to an oxygen bonded to an amine. So amide, as you might expect, all these amino acids will have an amide group because I'm calling them the amide amino acids. And they are both in the polar but uncharged category. So the first one is asparagine. So we're going to do 2 CH2s and then a carbonyl here and H2. This is asparagine. So to simplify the amino acid, 1, 2, 3. Asparagine. Could be spelling that wrong. The letter in this case is, I think it's N. The abbreviation is ASN. Okay. And no charge on amide groups. They tend to not get protonated, anything like that. So we'll put that as a new line here. And then how can we add to this? Well, just like we've been doing, why don't we just add a carbon before the main part of the group? Let's do that. Boom. And just by doing that, we already have our next amino acid, which is glutamine. It's GLN. So ASN was asparagine, GLN is glutamine. There's some parallel there. The letter is a little weird. It's Q. The way to remember this one, though, is that another name for glutamine, because it's so cute, is cutamine with a Q. So there's that one. Okay, moving on to our second to last group. We're going to look at the basic amino acids. So the basic amino acids are also known as the positively charged amino acids. This might be the last group, actually. That would be nice. So let's take a look. And of course, we already saw that histidine was an amino acid, right? And that's in our basic group because it gets positively charged. And generally, any N-containing, except for the amide-containing ones, are going to be basic. So we can actually kind of just build off this structure. That would be a little easier. So this amino acid has 4 CH2 groups before having an NH2 that often gets protonated to an NH3 plus. And this is 1, 2, 3, 4 NH2. I'll do NH3 plus. And this chain, this amino acid functional group chain, is so long that we call this one lysine. So L for long, L for lysine. This is, lys is the abbreviation, and K is the letter. Don't know why it's letter K. That one you have to memorize. Maybe, I don't know. Lysine, casein, something rhyming like that. K is close to L in the alphabet. That might help a little bit. Okay, let's modify this to make our final amino acid isn't that exciting. So this is I think this is the most complicated one. The first thing we're going to do is take off the NH2 and this last carbon, and we're going to put an NH here. Okay, next, another carbon, CH, might be a CH, might be a CH2. No, it's just a C, never mind. Another carbon, double bonded to an NH group that usually becomes an NH2 and gets protonated. and single bonded to a simple amine, which also often gets protonated. And this one is so confusing, it makes me want to go commit crimes on the high seas. So it is called arginine, like what the pirates say, you know? So arginine, letter is R, and abbreviation is ARG. And I'm realizing that I actually forgot 2 amino acids, so we're not quite done yet. So it's, is it 1, 2, 3 carbons, then an N, H, then an NH2 plus, then an NH3 plus. So arginine can actually have 2 positive charges. Fun fact about arginine is that because of that, it tends to migrate further on charge gradient gels than other amino acids. Yeah, I forgot a whole box. Okay, let's do the acidic amino acids. So, the acidic amino acids are very, very, very similar to 2 amino acids we've already covered, which are these guys. Our asparagine and glutamine, or cutamine. Their names are aspartic acid. So asparagine, oops, what the fuck was that? Asparagine, like aspartic acid, right? This one just has a hydroxide, or not a hydroxide, a carboxyl group, carboxylic acid, which is often deprotonated to make a negative charge. So this is a basic negatively charged, yikes, I'm off my game. It's an acidic negatively charged amino acid. So 2 carbons, then our carbonyl, then our carboxylic acid. Name again, similar to asparagine is aspartic acid. Oops. The abbreviation is ASP. The letter is D. One to remember this is a different way to pronounce aspartic acid if you have a certain accent would be aspartic, you know, with a D, aspartic acid. So there's a D there. Let's copy this guy. Oops, I said let's copy this guy. Jesus fucking Christ. Okay, it's going to be big. We got a lot of space. Okay. Then, as we have been doing for this whole exercise, we're going to just add a carbon before this main group, just like we did with glutamine, to make glutamic acid. See how that sounds like glutamine? Glutamic acid. And we'll do dot. Wait, what did I do it wrong? 1, 2, 3. Yeah, we're good. And again, it's also O minus sometimes. And because glutamic acid comes after aspartic acid, the letter is E, because E comes after D in the alphabet. And the abbreviation is GLU. And with that, our diagram and our exercise are complete. So practice this. You learn the amino acids pretty quickly. Might take 2 hours, 3 hours. Thank you for watching.